Broadly, this is what I have named, that flatness over Noetherian rings is too broad, but mostly what I would intend to talk about are the fiber conditions, and we would like to see the flatness in terms of fiber conditions. Okay, so let us start. And there would be some things which I would borrow from Professor Patil's lecture, Professor J.K. Verma's lecture. You will see. I will mostly, what I will do is I will just mention that without getting into the details, because that you either have learned or you are going to learn. Okay, it's like that. So instead of sort of going through the same thing again, we would just quote it, and then you will be able to identify it. Okay, I mean, somewhere down the line. Okay. Okay, so the local flatness criteria, this is how I would like to call it. And by the way, my principal reference for this part, this fiber conditions, etc., is Matsumura's commutative ring theory. Okay, so I start with a flat morphism, of R to R dash. I mean, they are Noetherian local rings. And our aim in this section is to investigate relationships between R and R dash and the fiber ring. So this is what the fiber ring is. I will come to a more formal definition soon. So mainly, I mean, see, we have already talked about flat descent, which is a very important concept. And we have learned in detail that what kind of properties behave well under flat descent, right? So here it is not exactly flat descent. Here, although I am assuming that it's a flat morphism, okay, but in this case, it is a bit more spatial. These rings are Noetherian local rings. And then we will see that if you have some properties of R dash, whether you can immediately say that similar properties hold good for R and vice versa. But we will see that it actually, many of these things do hold good, but with some condition on the fiber or on the fiber ring. This is the definition of the fiber ring. So this is the extension of the maximal ideal of R to R dash, and then you quotient a modulo MR R dash, okay, the extended ideal. Okay. So the first theorem, here you will see that I would require to talk about a little bit on this linear topologies and completion, but as I have already mentioned that I'll not get into the details because Professor Patil would be talking about completion. I'll just touch upon the bare minimum, mostly the definition, and then we will manage. Okay, it should not be difficult for you to understand because detailing would come later. Okay, so R is a ring, R dash is a Noetherian R algebra, and M is a finite R dash module. Suppose J is an ideal contained in the Jacobson radical. I mean, I am just using this a slightly different notation because I find it convenient, that J of R dash. Now, if you define Mn to be M mod J raised to n plus 1 m for all n greater than or equal to 0, and if Mn is flat over R for every n greater than or equal to 0, then M is also flat over R. Now, this is a very useful technical, well, you can call it a lemma, because we will see that immediately we will be able to derive some interesting consequences. Okay. Now, how do you prove this kind of a statement? So here we are not really relying a lot on the homological techniques. Well, it will come naturally. The Tor conditions, etc., will come. It's not unlikely, but you will have to do a little more work. I mean, like a slightly different kind of work. Let me put it that way. Okay. So first of all, it is enough to prove that for a finitely generated ideal I of R, the standard map is injective. So maybe I should underline it. Is injective, and I'm putting it in under E stroke T once again, because you know that wherever we have put this green underline, it means that it requires a little bit of explanation. Maybe I am a little silent about it, but it should be taken as an exercise, could be discussed in the tutorial and things like that. But can anyone give me a quick reason why? Have we done anything of this sort? That why is it enough to do it for a finitely generated ideal, or what is so special about this kind of a tensor product and then this map, this U? Do you remember? It's been a few weeks. I mean, can you see that? Why is it enough to prove that for a finitely generated ideal? By the way, I only have R dash is Noetherian. So that is why I'm just taking this finitely generated ideal I of R. I do not have any condition a priori on R. Okay, so do you remember, have we done anything of this sort?
Yes, we have to prove that because I is an ideal of R, and if we can prove that after tensing it is injective only for finitely generated R modules, then it is a flat module.
Okay, okay. So basically we are trying to prove that M is flat, and this is what was a technique, if you remember, in one of the earlier lemmas or theorems, however we called it, okay, that it is enough to do it for this, and then we will use this condition, okay, and see how it is done, how it is being done here. So, and also you have to notice why do we require that J to be contained in the Jacobson radical? Okay. Okay, so let us call it M dash. Then M dash is also a finitely generated R dash module. And then, so first of all, I'm saying that it's a finite R dash module, and hence M dash is separated for the J-adic topology. Now that's exactly where I said that I would be using a little bit of this language of linear topologies. So let me go through a quick kind of an introduction or brush up, whatever you call it. So let me take you here. So the left-hand side, okay? Look at the left-hand side. So this one. So let me just quickly go through it. Professor Patil will be addressing this. Any question? Nabukumar, do you want to ask something?
No, sir.
Okay. Okay, so so the quick kind of introduction to linear topologies in case you are not exposed to it. So if you have an R module, and if you start with a directed set, this lambda, and if you take a family of R modules indexed by this directed set lambda, okay, such that you have, whenever you have this lambda less than mu, then M lambda contains M mu, okay, then you can give a topological group structure. If we take this M lambdas, so you have started with a family of submodules of M, indexed by this directed set lambda, and then if you take this M lambda to be neighborhood base for 0, then this naturally gives rise to a topological group structure, okay, and then neighborhood base at X, you know how to do it, is very standard, that if you have, since you have started with a module, so naturally it is enough to give just the neighborhood base structure at the origin, and then you translate it, okay. So for any X in M, this X plus M lambda, lambda over this capital lambda, this gives you a neighborhood base with respect to any point X, okay. So this topology is separated or Hausdorff, that's what it means. So for our terminology, this separated is Hausdorff, or other as Matsumura takes it. And this is if and only if this intersection of M lambdas is 0. So we will have a detailed discussion coming up soon, because Professor Patil, I think, is going to do this completion in detail. Okay. Okay, so now a few quick facts. These are very easy to check actually. You could take these as simple exercises, that each M lambda is both closed and open. So what you get is, therefore, this quotient, if you go modulo this M lambda, then this would have, as a topological group structure, this would have a discrete this discrete topology. And then this, if you look at this intersection, then this is called a separated module associated with M. So a priori, if you assume that, just a minute. If you assume that intersection is trivial, then of course this is just M. So if not, then you go modulo the intersection and make it separated, and that is what is called separated module associated with it. Yes.
Sir, here you are taking closed neighborhood base. Means
Sir,
these things are.
No, why?
No, I want to know that are you declaring these M lambdas to be closed sets or open sets to get the topological group structure?
Open sets only.
Okay.
Open sets only.
Yeah.
Okay. Yeah. Now, oh, you mean why this is becoming closed and open both?
Yeah.
Oh, that you can check very easily. Okay, so you just take open neighborhood base, and this you can check very easily, this first bullet. Okay, and then this follows that it gives you a inverse system of R modules. So that means, and this is the map that since you know that for lambda less than mu, you have m lambda contains m mu, and therefore you have a natural R module homomorphism. So these are your maps, and this would create an inverse system of R modules. And then just take the inverse limit, which is called the completion of m. Okay, this m hat. So this is a quick kind of introduction, just because we need this language. And then here, now among the linear topologies, those defined by the ideals are of special interest, because that is what we will be using soon, because this gives a very interesting flatness criteria actually. So let M be an R module, and the topology of M is defined by this I to the power n m. Okay, so these are the submodules, and you can see that the directed set being used is this set of natural numbers, and you have this index family, you have that containment, and so on and so forth. And this, the topology generated by this, this family of submodules is called the eidetic topology. Okay, and if we give R the eidetic topology, then the completions, this R hat, this is the completion of R as an R module with respect to this submodules, the chain of submodules I to the power n. And then you have m hat, m cap, and that is given by these submodules. And then these are called the eidetic completions. And then you can prove these two, again, 2 bullet points, that m hat is actually isomorphic to m tensor R hat. Okay, and if R is Noetherian and I is an ideal, then R hat, the eidetic completion, is actually a flat extension of R. So these are the two, these are few very important facts that we will be using. I don't want to get into a more detailed discussion than this, because that is not required for our purpose for the time being. Okay, so now I would like to come back to this proof. So what did I say? So let me take you back to this statement. Here you are. Okay, so remember that we were proving that this each mn is flat, that is the condition given. And here you have these submodules, this j to the power n plus 1m, these are with respect to some ideal contained in the Jacobson radical. You have the flatness condition for each mn, then you are trying to prove that m is also flat. Now, how do you come to this kind of a statement? How do you prove this kind of a statement? Okay, so first of all, your m dash, which is a finitely generated R dash module. First, I claim that this is also separated for the j-adic topology. You know what separated means. That means when you take this, the indexed family, then the intersection is trivial. That's what we are using. So let us not get into the more detailed than this for the time being. Just assume that, yes, this is true, because the detailing would be dealt with very, very soon. Okay. So now we are trying to prove that this map U is injective. Okay. So take an element in the kernel, and we claim that X actually belongs to this intersection, but separated. Therefore, this intersection is trivial, and therefore X is 0, and therefore you are done. So that's basically the technique. Now, what does it mean by saying that X belongs to the kernel? Now, see, for any n greater than or equal to 0, you have this mn dash is basically this, right? Okay, so this is your definition of just a minute. Okay, yeah, this is your definition for mn dash. That is with respect to this m dash. Remember, this is your m dash. That is after you have tensored it with I. And then here we are using this base change. If you remember, in our first, maybe second lecture, we discussed this in detail, that if you have this extension R to R dash, then you can do this base change. Please don't mistake this as your normal transitivity. No. So base change, we proved it in detail. We showed how to use the universal property, how to define these canonical maps. And then you know that this will be isomorphic to this I tensor Mn. Okay. And this induced map Mn dash to Mn is injective. Now here, why did I say this? Can somebody come up with an answer? So I said, in fact, since Mn is flat. So do you see this really, that this is actually sitting as a submodule of Mn? So I'm using
So if I
MN is
take the I to R map,
right, exactly. So taking what?
I to R inclusion map, and then
Absolutely. So you have the map over here. Remember, your U is from here to here. Okay. And then what you have done is that you have just tensored with basically, see, this is you are tensored with this. And therefore, you have finally come to this. And because of the flatness, you naturally have that this is sitting inside this as submodule. Is this fine? Okay, fine. So if that is the case, then your picture is more or less clear. So you have this map out here. This is your M dash. M dash means, don't forget, M dash, maybe I should write it once. Often helps. So this is basically your I tensor M. This is your M dash. Okay. So you have this map out here, and then you have Mn dash. Mn dash is this, and you have your Mn. This is this, and then you have your map from Mn dash to Mn, and you have injectivity out here. So this is what you have proved using flatness of Mn, right? So let me highlight. So this is what you have proved, that you have an injectivity in the bottom row, and that is by the flatness of Mn that was given to you, and it follows that this. Now I have a question. The question is, where have I really used that it is contained in the Jacobson radical?
Separated.
Separated. So how can you be a little more explicit? Why separated?
Yeah, because if I take the intersection j to the power n and m dash, then using that Artin-Ries kind of argument, we can say that j times that is same as that module.
Absolutely, very good. So basically, we are using a kind of Artin-Ries here. I mean, since I am a little sketchy out here because Professor Patil is going to deal with it in detail. So this is where you need your J to be contained, because you do not have a local ring or you're not working with a maximal ideal. Actually, eventually we will specialize to local rings and local morphisms, but that is yet to come. So here your R is pretty general, absolutely nothing on, no condition on R. You have just the Noetherian condition on R dash. So here basically this part requires that J should be contained in the Jacobson radical. Okay, so just concentrate on this part for the time being, where we are using, I mean this part where we are using this flatness criteria seriously. You can accept this for the time being, or just have a quick brush up of whatever I have scribbled down, whatever I have showed. Just okay. Okay. Is it okay? Is it fine? Is this fine with you? If this was the proof we have discussed just now. Okay, so let me move on to this theorem. It's also very useful because gradually we are going to a very spatial situation and we will be using this. So this says that if you have a ring and R dash is a Noetherian R algebra, M is a finite R dash module, and suppose that B is M regular and it is contained in the Jacobson radical once again, because I am yet to assume it's local homomorphism, etc. And that is why I need that condition that it should be contained in the Jacobson radical. Then if M mod Bm is flat over R, then so is M. So you see, I mean, I was telling you, right? I mean, if you have, what we are trying to understand is that this opening remark, although it was a little general, little vague perhaps, that basically what we are trying to understand is conditions on R dash descending to conditions on R and vice versa. That conditions on R is giving rise to conditions on R dash, whether you have parity. Okay, and then we will soon see that this this fiber ring actually helps. Some condition on that ensures that certain conditions are preserved. So here you see this is a nice nice situation where you are showing that if you choose an M regular element contained in the Jacobson radical, okay, where M is an R dash module, okay, and then if you have flat condition over R, then you automatically have flat condition over R of the original module M, okay. So it's an R dash module, so naturally an R module as well. So this kind of situation you come across several times. So you kind of get into some kind of reduction step that you go modular regular element and things like that. And that is where these become extremely useful. Now proof, let us see the proof. You can guess what the proof is. It's not too difficult because we are going to use this theorem. We are going to use this theorem. So for each I, this sequence, so look at this sequence, m mod b to the power im, then m mod b to the power I plus 1m, and then m mod bm. You have this multiplication by b map out here. Okay, and because of regularity condition, etc., you have this exact sequence. And now by induction on I, it follows that this is flat over R for every I. Okay, is that part clear, what I said just now? So it follows that m mod b to the power im is flat over R for every I by induction on I. So where does the induction start?
For I equals to 1, it is given.
Absolutely. For I equal to 1, it is given because it is given that m mod bm is flat and it's indexed over I for I greater than or equal to 1. Right? And then what is that you are using here?
In the exact sequence, the second term and the second last term are flat. So using Tor ideas.
So this is flat. So let us take the I equal to 1 case. So this is your bm, m mod bm, and this is flat. Now here m mod b square m, and then here again m mod bm. And then what will you do? You will move on to the long exactor.
Yeah, there. I mean, so for any 3 terms, 2 of the n terms will be 0. So the middle one must be 0.
So you have automatically the middle one being 0. Absolutely. So please remember, this was my comment when I was talking about homological techniques, that whenever you have this kind of thing, use the derived functor, move on to the long exact ector or x, wherever what is necessary, and then see the 0 condition on these derived functors. Okay, on these derived, functor modules. So that is the technique. So always move on to the derived, move on to the long exact homology, and then just argue through the 0 condition. That is how you manage. Fine. Yeah. So therefore, it follows that each one is flat because the Tor should be vanishing. And then by the previous theorem, we get that M is flat. So see, now you see that how basically you use this kind of a situation. Now, again, once again, the question would be that why do you need that B to be an irregular element contained in the Jacobson radical? That's kind of obvious because your J ideal has to be contained in the Jacobson radical. Otherwise, we don't have that separated condition. Okay, so that is the reason, just in order to use this. Okay, can you guess a kind of a spatial situation where I can avoid this Jacobson radical condition?
Local rings.
Local ring, absolutely. I mean, that's the most obvious choice, and that's exactly which would sort of take me to. Okay, so let me now. Yeah, so this is what I have just given a quick introduction to this linear topologies. Yeah. Okay, now I'm coming to a little technical definition, but it's not difficult to understand why you would require this technicality. So let R be a ring and I be an ideal, absolutely general, as you can see. An R module is said to be iadically ideal separated, okay, if this module is separated for the iadic topology for every finitely generated ideal A of R. Basically, you keep this theorem in mind. Okay, this theorem will actually set the background up very clearly. That you are kind of creating the necessary conditions which you would be using. Okay, so for example, if R dash is Noetherian R algebra, and if you have this I R dash contained in the Jacobson radical, just a situation like here, then a finite R dash module is iadically ideal separated. So this definition is kind of a little, you can say, motivated by this. Probably you will get to hear this again in Professor Patil's deliberations, but I'm not sure. Okay, so just following Matsumura's terminologies. So this is the definition. So basically this is to sort of make this kind of a theorem work. That is the whole idea. Okay, so see how it is being used. Maybe I'll keep this definition open. Yeah, so this is the definition of iadically separated, ideal separated. Yeah, so now I'm just stating a theorem without proof because I don't want to get into the detail checking. For the time being, you just accept it. If necessary, I'll add a proof later on. but we don't really need it in full force. That is why I felt that maybe I can just sort of make a quick comment. Okay, so it says the following, that suppose that one of the following two conditions is satisfied. By the way, these are the notations I am using. This Rn is R mod I to the power n plus 1. I is an ideal. I don't require much conditions on R really. You will see soon. Mn is m mod I to the power n plus 1 m for n greater than or equal to 0. This is so you know this is, you know what is, do you know what is this? So if you take I raised to n mod I raised to n plus 1 and take the direct sum over n, do you know what this GR are called?
Associated gradient with the ionic filtration.
Absolutely. Similarly, for M also you have this the module version of it with respect to it. So everything is happening with respect to I-adic situation. Okay, because your the family of ideals that you are starting with, or the filtration you are working with, is I to the power n. Okay. So now suppose, so this is the terminology. Rn, Mn, do keep in mind, and then you have GRR and GRM. Okay, so if one of these conditions is satisfied, so one is I is a nilpotent ideal. What is that? What is the definition of a nilpotent ideal? And how do you think it might help? Okay, maybe I'll come to that. Okay, or if R is Noetherian and M is I-adically ideal separated. So I told you, right? I mean, I basically want that theorem to work. Basically, if I have this flat condition on M mod J to the power n plus 1m, and then I want to have the flat condition on M. So that is why this I-adically ideal separated kind of condition is required, because you know what this is. Basically, this means that each such tensor product is actually I-adic, is separated for the I-adic topology. So if you have that, then you have this bunch of statements, and they are all equivalent. So I would like to draw your attention to some particular parts. So you see, so what is interesting here is that, so what is the speciality of this theorem, right? So aim is, so once again, I am basically trying to, find out when is, under what conditions aim is R flat. Okay. Now look at this. So here you have this condition. So look at B, then look at D. Okay. Again, you look at E, F. So all these are statements involving only R0. Okay, involving only R0, which is very, very special in the sense that if your R was a little more spatial and I was a little more spatial, for example, R is a local ring and I is the maximal ideal, then itself you know what your R0 is. Okay, and then automatically freeness would imply flatness, and you can invoke that theorem which we have proved just now, that if you have M mod J to the power n plus m is flat, then you have flatness of M. So this is a kind of a much generalized version of what we have already proved. And here this kind of spatialization, that all these conditions are with respect to R0, makes it really spatial. So that is actually what this speciality of this theorem is. So since I do not require the entire thing, so I just skipping the proof for the time being, just take it in its face value, and then I'll add a proof later on. Okay, so let me keep this theorem open here. Yeah, and then see what we would like to do with it. So basically, let me go there. But okay, a quick recapitulation of some terminologies about local rings. I'm sure you know this. So a local homomorphism, you would see this name coming back again and again, because our main focus would lie on Noetherian local rings. Okay, so what is a local homomorphism of local rings? It means that it's a ring homomorphism from this local ring to this local ring, such that the maximal ideal is contained in this maximal ideal. Okay, so this is the definition of a local homomorphism of local rings. Now, two quick lemmas. One is that if you have a ring R, you know this, of course, that these conditions are equivalent for a ring to be local. So one is this Pekar has only one close point, namely, you know, the maximal ideal, there's only one maximal ideal. Then you know that this R has a maximal ideal and every element outside M is a unit, and R is not a zero ring, and for every X in R, either X or 1 minus X is invertible or both. So you know what this means, that this for a ring to be local. And then another one is involving this ring homomorphism. If you have ring homomorphism of rings R and R dash, suppose they are local, then the following are equivalent. That you have a local homomorphism means this phi maps MR to MR inside MR dash, and then the contraction of MR dash is MR, and X in R and phi X is a unit in R dash implies X is a unit in R. Take these as small exercises and work it out. These are kind of very, very standard facts. I thought that I would just have a quick recapitulation. Okay. Now, what do I want to, how do I want to use this theorem is the following. Okay, so look at this remark. So this theorem is particularly useful under the condition that R is Noetherian local and I is the maximal ideal. How? In this case, R naught is a field and M naught, because R naught is, you know what it is, it's R mod M, right? So this is a field and M naught is automatically flat over R naught. Okay. Also requiring Mn to be flat over Rn. Oops. Yeah. So also requiring Mn to be flat over Rn. Here you are. Let me see where I mentioned this. Is the same as requiring Mn to be free over Rn. Okay. So just a minute, please. Okay. Yeah. Sorry, there was a small hitch. Okay. So so basically your conditions that every time you are specializing to R0, and that kind of being a field for a Noetherian local ring. So your flatness would be kind of automatic. Then requiring Mn to be flat over Rn is the same as requiring Mn to be free over Rn. Can somebody tell me why? So this is Mn is Rn flat was our last condition, condition G. Is saying that requiring Mn to be flat over Rn is the same as requiring Mn to be free over Rn. Why is that so? Assuming that R is Noetherian local and I is the maximal ideal.
Sir, modules over a Nigerian local ring are flat if and only if they are free.
Local ring, yes, but I mean, Rn, is it local still? Can you just give a quick explanation? Rn is this. This is Rn. R mod M to the power n plus 1, right?
Yes,
So,
yes.
yeah, so that will
It
also,
is.
yeah.
It is also a local ring. M by In plus 1 is the maximal ideal.
So this is the spatial situation that we were talking about. Okay. So this looks pretty general, but that's exactly what I was trying to say, that I don't need it in full force really. I need it for this very condition. So now we are here that suppose you have Rm and R dash in a local Noetherian rings, and these are their respective completions. And here you have a local homomorphism. I'm talking about this line. Okay. Now for a fixed R dash module M hat, we have already quickly discussed what we mean by this, but best is to see this like this tensor product with respect to this extension. Then M is R flat if and only if M hat is flat over R, and then M hat is flat over R dash. Okay, so and let me also show you the next statement. So let M star denote the MR dash at a completion of M. Then we have M is flat over R. Then M star is flat over R, and then M star is flat over R dash. Okay. So you will see some use probably later. Right now, not so much, but I thought that this is the best place because this way I can show you that how you can, under what conditions you can play with flatness. Okay. I mean, for what kind of extensions you have the flatness going there, and then whether you can come back and things like that. So basically, how do we prove? I'm coming to it in a minute, but just understand the statements well. So you have these local Noetherian rings, and you have their respective completions, and you have a local homomorphism. So what it says, this R flat condition, you can easily move from R to R hat. Okay, the flatness is actually a very nice condition here if you are talking about local rings and your normal emetic completions. Okay, so this flatness here, flatness here, flatness here, these are all equivalent. Okay, and similarly, if you take, so M star is not your M hat, because that was that, you understand what I mean, that this was your completion with respect to the respective maximal ideals. Here what we are saying, that if I just take the extension of this maximal ideal to R dash, and we take the MR dash edic completion of M, that is M star. Then also interesting fact is that then also you have similar thing happening, that you can safely move from R to R hat, okay, and with respect to M star, okay, not just with respect to M hat. Now, proof is actually very simple because we have done the necessary groundwork. So the first equivalence comes from the transitivity law of flatness, together with the fact that this R hat, R dash hat is faithfully flat over R dash. And the second equivalence follows from both the sides equivalent to this being flat over R mod M to the power n for all n positive. Okay, so this this equivalence, this what I said here, the first equivalence comes from the transitivity law of flatness is fine. But can somebody tell me why I suddenly said that the second equivalence follows because both the sides are equivalent to this being flat? What is that I am using here? This, please look at this statement. The second equivalence, what is the second equivalence? This is the second equivalence. This flatness over R and flatness over R hat. And we are saying that we have taken what? We have taken M hat, which is an R hat module, obviously, of course, an R module as well. So we are saying that this equivalence follows from this fact that it is actually equivalent to this being flat. Can you tell me why? What is that I am using here?
I think in first limit.
Say it again, please. Your voice is not clear.
Like I think it is follows from inverse limit you have said earlier in completion limit.
You mean the first statement that I proved?
No.
Or are you using this theorem? Because your Rn is something very, very special, by the way, here. And I don't have, although you are working with the local ring here, so that's a good thing. So your Jacobson radical is being taken care of, but you have a more specialized thing to work with. So is it that we are using this one somehow, this theorem? Are we using this? Okay, so think about it. Maybe I'll just again, let me see. Yeah, so let me take this.
Sir, are you using the A to G equivalence in the left hand side?
Which one? No, this equivalence.
No, I mean to conclude that statement, are you using the A to G equivalence on the left hand side of your screen?
Yes, precisely. So that's exactly what I was trying to say, that A to G equivalence is what we are using. So, but can you see this? I mean, you should be convinced. So here, A to G equivalence is what we are using here, because here your basically what we are doing is, what is your conclusion? What do you want to prove? You want to prove that M hat, your module is M hat, which is an R hat module, right? And therefore, so you want to conclude that M hat is flat over R and flat over R dash is equivalent. Okay. Now you come here. Okay. So basically you have your, what you need to be careful about is, where do you see the R hat here? That's the only thing that you have to be careful about. Where do you see the R hat here in this whole statement? There is no explicit mention of R hat, right? You have an R module and you have this, but it's not difficult to guess, right? You want to conclude about R hat means basically you know what your R hat is, and now how this kind of condition on each, you can say on each piece, flatness condition on each piece giving rise to the flatness condition on the entire ring. So just try to see where, how do you fit in the R hat here? That's all. That's the only thing that's what requires an explanation. So I am putting it under E stroke T.
Sir, Mn hat and Mn are isomorphic, right? And similarly for Rn.
Yeah. Yeah. So I need this detailing. I need this detailing. Okay. So please give the detailed explanation and we will take it up again for the tutorial. Okay, so please pay attention to this. And let me go to the second one, and then I'll again come back to this theorem once. So the second one says that your M star, if you remember, M star was the completion. Yeah, M star was the completion with respect to this ideal, MR dash. This is an MR dash at completion. Okay, and then you are saying that all three conditions, they're equivalent to this being flat. Are you convinced again? Are we using this theorem or something else? Or are we using the first proposition? If you want to recall, then let me take you there. This was it. Your contained in the Jacobson radical is more or less taken care of. That's not a problem, right? So are we using this or that theorem? So this, I'm putting this as a small E stroke T. You just have to figure out, where do you see the R hat coming here? That's the only thing. It's not difficult to guess. Actually, it's very easy to guess. Only thing you have to note is that here your R dash, here this is your R dash. So you have from R to R dash, R hat, you have this morphism, and you know this is a flat morphism, okay? And therefore you will be using that together with the fact that if you have the information of the flatness of each Mn, that gives you the flatness of R, or flatness of each Mn over, let us say Rn, that gives you the flatness over R of this M, and then you use this one. Okay, so this theorem coupled with that later theorem is what you have to use. So your map, the extension that I am talking about is R to R hat. That's the only thing you need to be careful about. Once I am talking about M-adic, another time I am talking about M-R-adic. That's the two things, but they are the same thing. Essentially, there's hardly any difference. Okay, so please convince yourself. Otherwise, this has been already marked. So this will be again taken up in the tutorial. Okay, so now, yeah, kind of little more focused. Now you have Noetherian local rings and you have local homomorphism. You know what this is. Oops. So let me use this. So the local homomorphism. And U is a morphism of finite R dash modules. Then if N is, suppose that N is flat over R, and then the following conditions are equivalent. that U is injective and N mod UM is flat over R is equivalent to saying that U hat, U bar after this tensoring is also injective. You will see an use of this basically. Okay, this will be a very nice technical step which we will be using soon. So please have a look and see that which part is kind of easy. Already you can see 1 implies 2 I have put under E stroke T. But can you quickly explain 1 implies 2, how does it follow? I have Noetherian local rings and the local homomorphism and finitely generated R dash modules and a morphism of finitely generated R dash modules. So how does 1 imply 2? 1 implies 2 follow. K is of course your R mod M that I should have mentioned there somewhere. Yeah, yeah. So do you want to see the kernel? Okay, so let us say that 2 implies 1 first. So 2 implies 1. So if you have this injectivity after tensor product, so you can see it's a kind of going back, right? So it's a very important, that's what we have discussed at length when we talked about flat descent. So if you have this injectivity after tensoring, then whether you have the injectivity without tensoring, okay? Now this is not as it is not true, of course, but with this extra condition, it is true together with the fact that N is flat. This is a very, very, very important kind of a proposition which you keep using. Okay, so you have this kind of situation. You know, often you have to do a base change. You have to make an extension of base. So if you have after extension of base, if you have injectivity, do you have injectivity of the original map? Yes, it is, provided you have this and this. Okay, and of course under the condition that you have a local homomorphism of local rings. So how do you prove this? 1 implies 2 is actually easy, but you take some time to think over it. 2 implies 1. So you start with an x in M such that it is in the kernel. Then you have u bar x bar equal to 0, so that x bar is 0 and therefore x belongs to MM. Okay, because this is the tensor product, that is M mod MM. Okay, so now let me take you to this statement. Yeah. Okay, suppose x belongs to m to the power nm, then we will prove that x belongs to m to the power n plus 1m. You know which direction we are moving to, right? Now, what we do is, you start with a minimal generating set for m to the power n. You have nice everything. I mean, like you have Noetherian local rings, so you know that you can actually talk about it. And then write your x as summation ai yi in m, because you have ux0, u bar x bar 0, so you automatically have this, and n is flat. So there exists Cij in R and Zj in N such that this is true. Now this is something which we have not talked about so far. So we have mostly seen flatness with the help of a derived functor. We have seen this with the help of Tor, etc., etc. Okay, so we have given rise to a short exact sequence, and we have tried to understand that a flatness through a vanishing of derived functors. Now we are, in a sense, talking about it a little loosely, we are seeing it more internally, that playing actually with the ring and actually with the module. So here you have a nice condition which says the following. So I have put it under E stroke T. By the way, this will be a part which will be definitely discussed, but I will add a proof in detail in these notes itself. Okay, for the time being, let us just use it. So if you have a ring R and M is a flat R module, suppose that you have this coefficients Aij and Xj are in M, satisfying. So you have some linear relation being 0 among these Xj's. Then there exists an integer S and Bjk in R and Yk in M, such that you have that for j in between 1 and n and k in between 1 and s. Don't worry about the indexes now. I mean, just see what is the main thing that it is trying to talk about. You have this aij bjk is 0, and xj can be actually written in terms of these yj's, okay, which you are talking about. You claim that they exist for all j. But you will soon see that this is actually more powerful than you actually think it is. That a very simple linear vanishing condition giving rise to flatness. That's exactly what we are trying to do. Okay, a kind of a linear algebraic condition, you can say. So this is what we will be using here. This is what we want to use here, and we will discuss a proof later about this one. So let me use this. So what we are saying is that you have this 0 condition, and as you can see, these uyi's are this xj's basically, right? So if you have this, now you have flatness, okay, of n. So you claim that there exists Cij and Zj such that these uyi's, you can actually write them as linear combination of elements in n. Okay, please don't forget here your map is u from m to n. Okay, and therefore your uyi's, these are in n, and basically what you are doing is you are trying to see them, these uyi's, for this kind of a linear vanishing condition. You are able to see that these uyi's, you can see them as linear combination of some elements of n, if you assume that this is flat. So this is what this theorem tells us. But this theorem actually tells us more. We will see this a little, not today, in either one of the tutorials or in my next lecture. Okay, so now if you have this, then are we done? We are trying to prove that U is injective. Okay, this is what we are trying to do with this and this conditions. That n is flat and n mod um is flat over R. So if you have, and we have used the flatness of n, and we have used this this theorem, and we have come to this kind of a situation. Are we done, or still some more work has to be done? Can you see carefully? I mean, in this case, this flatness will come. That's what I intended to say. So this is not a condition. I mean, now I'm trying to prove this actually. There's not just this injectivity of U, we will also get this. So are we done from this point, or?
Shall we need to show that yi's are 0 using the minimality condition?
Okay. So, no, y is a 0 using the minimality of what? You have a
That
minimality
minimal
here.
basis.
Yes. You have a minimality here. Okay, so yeah, sort of close. So let us. So let me open this. Keep this open. Yeah. So by choice of A1, A2, AR, all these Cij's are in M. So please don't forget where your this Cij's are. Okay. So UYI's, here you had this, And don't forget that this is basically a minimal generating set of this, a minimal generating set of this R module m to the power n. Okay. Now, why am I saying this? All theCijs are in M. Is that clear to all of you? Aijs are generating m to the power n.
If some Cij is not in M, it is unit. So we can, from this equation, summation AI Cij, we can express one of the AI in terms of the other AIs.
Very good, very good. So that's exactly where you are using the minimality, as he was trying to say. Okay, and therefore your UYIs, they belong to Mn. That is clear, because this if you say that they are in all in M. Okay, and your URYI bar is 0. Okay, so that this is 0 and yi belongs to mm. Is that clear to all of you? Why am I writing this? We are trying to prove 2 implies 1. Okay, so fine. This is fine. This is basically the injectivity condition. So you have yi belongs to mm, and therefore x belongs to m to the power n plus 1m. Okay, but remember what is that we were trying to show? We want to show x is 0, right? We were trying to show that if x belongs to m to the power n m, then x belongs to m to the power n plus 1m. But then your work is done, because you started with what? Started with x belongs to mm. Therefore, you have proved that x belongs to m to the power nm for all n. And that's it. You have therefore here, and that you know is 0, you have the separated condition, and therefore you have the injectivity. Okay. Now this extra thing that this is also flat, well, that is easy, because you already now you have this, that here you have the flatness, and you take this short exact sequence, get into the Tor. Okay, so once you go to the Tor, and then you have this is vanishing, and therefore you have this is flat over A. Okay, so with a modest assumption of flatness of n, and the fact that Noetherian local rings and local homomorphisms, this basically gives you that how to go back from this. Go back means if you have the injectivity after tensoring with K, then it actually gives you the injectivity without tensoring and something more. Okay, and this is basically happening because of this flatness. And if you want to come from here to here, then injectivity together with this flatness ensures, but this I have not discussed. I have kept it as an exercise for you, and it will be taken up. If you give it a try, if you don't get it, of course it will be taken up. Is this clear? Is this proof clear to all of you? So this is something which we have used, and this also will be taken up. Is this fine? Okay. So a corollary to this, once again, I have kept it as an exercise, because these are some simple things which you should be able to figure out. That if you have Noetherian local rings, if you have Noetherian local rings and local homomorphism, and if M is a finite R dash module, and if your this R dash bar, I'm using this notation bar to denote this R dash tensored with K, and K is R mod M, of course. And for x1, x2, xn in n, if I write the image xi bar in R dash bar, then the following are equivalent. That x1, x2, xn is an M sequence, and this Mn is flat. This is your Mn. If and only if x1 bar, xn bar is an M tensor K sequence, and M is flat over R. Now this actually, you can probably see how it follows from this theorem. Look at it carefully, and then see if you can understand it. Is it a kind of a quick application of this theorem?
So for the first element, I mean, the first condition on the left hand side is giving is almost equivalent to the first condition on the right hand side, right?
Yeah.
And so the second condition follows, and then we have to apply induction.
Right. So you just do it stepwise. Okay. Your M sequence, you know what it is. So therefore, you have used the non-zero divisor every time, and therefore you have to use this injectivity. Okay. Good. And the second one as well. But is the second one is a kind of a ditto of the second condition there? So the injectivity of U bar, and you have this flatness out.
Here U is, I mean, U maps from M to M is the multiplication by xi sort of thing.
Absolutely. Not sort of, exactly that. I mean, like that is you have to do that. Okay.
Yeah.
Yes.
And I mean, for every step, I have to go modulo that and then multiplication with the next element.
Yeah, but my question is here, you need this flatness. Where do you anticipate that would play a role? Once you do the detailing, you will see, but can you just quickly anticipate? Where is this M flat is working? Suppose I am trying to go back from 2 to 1, okay? That if I have this, because see, that's exactly what I was saying, no? You may have to change your base, extend your base, and then do make a conclusion over there, which may be easy because you can see that you are tensoring with a field and you are in a local ring setup, so quite many good things happen. So therefore, maybe this is easy to derive, and then I want to go back to the original one. But I'm saying that flatness, where do you anticipate that it would come? So why don't you just take the sequence of length 1 and see? Instead of seeing it, the entire thing, just take a sequence of length 1 and see what is happening. Okay, so you just have an M regular element, and then you are going tensoring with K, and then going to Xi bar, and then you want an regularity after tensoring. Okay, so then you will see that how this flatness is playing a role. So that's exactly what you need to be careful about. Okay, so this is, as you can see, that this condition, this is very easy to guess that this map is basically going to be your multiplication by this each xi. That is clear. But what you need to be careful about is this portion. Okay, so where exactly this flatness is being used. So do this n equal to 1 case, and immediately will understand, and then you will know how to proceed. So putting under E stroke T. So and I'm going to put quite some of these in the tutorial sheet, and it will be discussed, and please go through them. Please try to prove them on your own, and they will be taken up again. Okay, now yeah, look at this. So you have a Noetherian ring, and you have a Noetherian R algebra, and M is a finite R dash module. Suppose you have an element in R dash. Now, if you have flat over R and B is regular for M mod, this M intersection R for every maximal ideal of R dash, you know what this means. By this we mean the contraction. Then B is M regular, and this is flat over R. By the way, this we need these things. I mean, these are kind of some small technical steps, And then gradually we are moving into something like, for example, what we see here. Okay, so here what you need to carry with you is that you have a morphism of finite R dash modules, and then under what condition you have the injectivity being preserved even after tensoring by this R mod M. Okay, because soon you will see the fiber thing coming up, and then you will understand it even better. But right now you don't see the fiber. Okay, but we are just talking about tensoring with respect to K and things like that. So here basically you see how your injectivity is being preserved. Okay, originally and then after tensoring with K. This is what the importance of this, where the importance of this theorem lies. And then you see here, this is a nice application of that in terms of the regularity. Okay, regular sequences. Now what you see here is that if you have under what condition you have the regularity of some element, and also like the flatness when you go modulo a submodule which is of this sort, Bn. Okay, so let us quickly see this proof. So let us denote this. So what is that we are trying to prove? So let me highlight the portion, just a minute. Yeah. So this is what we are trying to show, that if we have the regularity for this, okay, then we are trying to prove that B is M regular and this is flat. So you start with this multiplication by B map, and K is the kernel. Then K is 0 if and only if Km is 0 for all maximal ideals of R dash. Is this fine? Is this fine? This is, you know, the local global. Okay, M is a finite R dash module, and you have the zero condition on this submodule if and only if the zero condition after localization. So B is M regular if and only if B is MM regular for every M in max spec R dash. Okay. Moreover, R flatness is a local property, you know that, right? Even after localization with respect to every prime or every maximal ideal, this is true. So in R and R dash, so one can replace this R dash by Rm dash, okay, for M in max spec, and R by, you take the contraction of this maximal ideal for R, and then you have this by, and replace M by MM, and the case reduces to the previous theorem. Now, what is that previous theorem? So the previous theorem is basically, you can also treat it like the special case of this corollary, right? So do you see how basically we are invoking this corollary, or you can even take that map U, etc., and the injectivity. So do you see what is happening out here? What reduction step we have taken? Now, this is a very standard technique in commutative algebra where you often see whether it is a local property, and then you localize and assume that your rings are local rings, okay, with respect to suitable. I mean, like you take a maximal ideal here, you localize, and then you take the contraction, you localize. So do you really see that you have local rings and this kind of a situation here? Please don't forget that here your R and R dash are local Noetherian rings, and this is a local homomorphism. So when you have localized R dash with respect to M M is a maximal ideal of R dash, and then you have taken the contraction and you have localized R with respect to that, and then you safely changed M to MM, because you know why? That flatness and the zero condition, everything, they are equivalent to being the flatness or zero condition of the original module. So do you see that you have really local Noetherian rings and local homomorphisms?
So the role of R and R dash in the right side page is being played by these two things in the left side page, right?
Two things means
R M intersection R and R localized at R prime localized at M. And you are taking the image of B as this Xis.
Yes, no, first of all, see here you have a Noetherian local ring.
Yeah.
Okay. And what about this? Is this also local? This R localized at the contraction of M on R? Yes. So how is it exactly a kind of a situation like this is what my question is. So when you have this M intersection with R, do you still have local situation? Because see, otherwise, I mean, like I need Noetherian local rings, that is for sure, and local homomorphisms. Yes. So if I have a local homomorphism, okay, I have a local homomorphism, and then if I contract the maximal ideal from the right hand side to the left hand side, what do I get? Phi is a local homomorphism of local rings. You know what that is. And then if with respect to that, if I contract the maximal ideal on the right hand side to this, then I do get a prime ideal, but anything more than that you can say?
The maximal ideal of R.
Exactly. Okay, so first of all, therefore, if I take a maximal ideal out there and then a contract, then I do get, after localization, I do get Noetherian local rings and local homomorphism, no doubt, right? Isn't it?
Yeah.
So that's the first thing. And then what you need to see is what I was trying to tell you, that here next what you will do is you will start with an element. You will start with a finitely generated R dash module, and then for each regular sequence, for each x1, x2, xn, you will take these xi bars in the images there, and then you will conclude about this. So obviously, just imagine the condition for n equal to 1 and see how it translates. Okay, so if I start with, and here I just have Noetherian rings, and R dash is a Noetherian R algebra and finite conditions. So you are basically coming to the local situation by localizing with respect to maximal ideals, and then you are giving rise to this local Noetherian situation, and then you just use this what you have already proved. Okay, so just go through it and you will understand. It's kind of, it's a very nice reduction process. Yes.
For this R localized at M intersection, and this is local because this M contraction is a prime ideal.
Yeah. This one is just, see here, I do not have a priori any local condition on R and R dash. So
No,
I do not have maximality here. But what I'm saying is, once I have local rings, then you just need to check that you also have a local homomorphism, isn't it?
Yeah.
And then you take just this M and M, you just take etc., and then you apply this one for this. Okay, so here you have proved it, and you just prove it for one element. Okay, okay. So now how we use this? Yeah. So you have a very important, very important corollary that you have a Noetherian ring, and this is the polynomial algebra over R in the indeterminate x1, x2, xn. Okay. Take an element fx in R dash. Now, if the ideal of R generated by the coefficients of f contains 1, so if it is the unit ideal for a particular polynomial fx, then f is a non-zero divisor of R dash, and R dash mod fr dash is flat over R. The same thing holds for the formal power series ring. If you take this, sorry, I meant to write, just a minute, let me correct it. Yeah. Okay. So first of all, see, this you can probably guess by now that how we are going to manage this. But anyway, let us go through the steps. It's not difficult because we have proved almost everything that we require. So this is a free and hence a flat R module. Okay, and the formal power series ring is also flat. By the way, here, this is an exercise. This I have kept as an exercise only, and this will also be added. So this is an exercise from Matsumura's book. So this, when you do the flatness for this formal power series, then you use this. You can use this kind of a condition that Noetherian ring, and you have family of flat R modules. The direct product is also flat. In particular, this is a flat R algebra. Okay, so anyway, you need the flatness. Fine. So you have your polynomial ring, or the corresponding parallel is the formal power series ring. Now you see how you prove it. Prove this. Yeah. So for a prime ideal P in spec R, if you go mod P R dash, the extension of this prime ideal in R dash, then you know this becomes this. And in the formal power series ring, we have this. Of course, this is true in any case. Since P is finitely generated, don't forget that I have the Noetherian condition. Okay. So do verify these things, please, once, if you are not sure. Okay. So you have in the formal power series ring also, you have this. Do you think that this was necessary? I could have simply dropped that finitely generated thing in the formal power series ring. Do I really need that finite generation so seriously? Anyway, we'll come to that. Okay, so now what I'm saying is that in both the cases, this R dash mod PR dash is an integral domain, so that the assertion now follows from the theorem. So which theorem? So again, let me take you to the statement. So of course this theorem, but you can, not difficult to guess. But how? So this is my theorem, and this is my statement. Where have I used this condition that the coefficients of f contain 1, and we are trying to talk about non-zero divisor condition of f on R dash, and I am saying that just take a prime ideal and I have integral domain, and therefore this follows from this theorem. How exactly? How is this condition being used? Where have you used this flatness? So maybe I open this corollary here and take you to this. Yeah, this proof. Where exactly, why suddenly a prime ideal in spec R? So the theorem is this one, the corollary is this one. Okay, so question is therefore, okay. So please have a look at it carefully. I'll have to come back to it. Okay. So you see, I told you, right, this is going to be a technical step for proving something very, very important, that we are specializing to a very, very special situation, namely polynomial and power series ring. They are flat. Okay. So therefore, they are flat extension of the base ring. That's what I mean to say. And therefore, many things should go through. But I mean, just proving them automatically does not happen. I mean, like it kind of requires some bit of effort. And here, what you can see, what is very, very interesting is that we are definitely using homological techniques. We are using Tor, vanishing of Tor here and there. But more importantly, I mean, we are kind of playing with this module. And I would like to again point out some important parts. So for example, see here, see this argument. This argument is very, very nice and classical, that for showing that something something is zero, some element x is zero, you are basically, what you are showing is that it is belonging to all m to the power nm, and therefore the intersection is trivial because of this, the separated condition. Okay, so you see, this is like you are actually playing with the elements and the submodules there. Okay, this was one instance. Keep this in mind. Then I'll show you one more instance. For example, let me take you there. Yeah, you see. So, I mean, it's essentially the same technique. If you just go between the lines and see it, watch it carefully, you will see that essentially the same technique, that here you have again the vanishing condition coming because of the separatedness. And therefore now what you are doing is that you have the situation which is after tensoring and before tensoring, and how do you manage both. Okay, and commutativity of the diagram, injectivity of some map at some level, and then the commutativity, etc., takes care of it. So you see, I mean, like these techniques are slightly different, where you are definitely using homological ones, but also something more. Okay, so here you see a very nice instance. Yes, here again, this statement, if you remember, I have kept some E stroke T's for you to go through in detail. Again, they will be taken up in the tutorial sessions, that I'm saying that this follows because of flatness. And I told you, right, I have a long technical lemma where many statements are equivalent. And I have also proved this very important theorem. And I said, if you couple them and see them carefully, you are there. So this IADIC kind of technique is what is principal for our this part of the talk. Okay, here another very nice instance. This will be taken up in detail. What I will do is I'll add it in the tutorial sheet with some ample hints so that it's kind of almost proved but not quite. So this is another instance. You will see that you are playing with the elements and you are how to manage and how to use flatness cleverly. Okay. So, and finally to come up that this statement that how do I use this corollary, okay, use this theorem for specializing in this context of polynomial and power series. Okay, again let me move on. Now let me quickly bring in fibers, and but I will not be able to go a long distance because I need regular local rings. But let me at least go up to that point and then stop. That so you have Noetherian local rings, local homomorphism. Now this is the formal definition of fiber. So you take this R dash and tensor it with R mod M. Okay, so this is what is called the fiber ring. You will see, find it very interesting to see that this conditions on the fiber ring, okay, actually helps you go back and forth in between this R and R dash. Okay, if you have flatness, etc. Okay, how to see this? So let us take this theorem first. Again, I'm not going to give a proof of this now. This will be discussed later. That if you have a homomorphism of Noetherian rings, and if your P is in a prime ideal of R dash, and little p is the contraction of capital P, little p is the contraction of this capital P, then you have these two things true, that the height of this prime ideal in R dash is less than or equal to the height of the contracted ideal plus this dimension. And if phi is flat, or more generally, if the going down theorem holds between R and R dash, then equality holds in 1. So it probably, you have already seen this in Professor Patil's lecture, I'm not sure. So I have not immediately added a proof, but I can add a proof, or if you want, we can also have a discussion. Right now, as I have said, that there will be certain overlap. So I'll just kind of quickly browse through it, but if necessary, we can always come back. There's absolutely no problem. Accept it for the time being. Basically, I need some comparison between the heights and the dimension, etc. When you have a homomorphism of rings and when you have contraction of ideals, etc. Now, how we use this is exactly here. So the following theorem gives a kind of converse under certain conditions. So what kind of converse? I'll see that it says if you have R, R dash and F as above, what is this as above? What does that mean? So this is the one, okay? So your R and R dash are Noetherian local rings and you have a local homomorphism, and F is the fiber ring. If R is a regular local ring, and R is Cohen-Macaulay, and dimension of R dash is dimension of R plus dimension of F, then R dash is also flat over R. So basically, we are trying to get a flatness criteria using properties on R, R dash, and F. That was my opening remark, that what kind of conditions on R, R dash, and F, or rather, what kind of conditions on F would ensure that certain properties between R and R dash, some parity is maintained. So this is what we would begin with. But I will first introduce regular local rings, and then I will come back to a proof of this and a lot more. Okay, you will see them. In fact, certain parts you have already probably seen in Professor Patil's lecture, also probably in Professor Chekivi's lecture, or you would see. So we will see like how we use regular local rings conditions. Basically, system of parameters kind of arguments would be used. So we will see that subsequently.